So, this week we will be talking about Simulink. And, well, basically most of the time, if I'm talking about Simulink, I'm not actually covering the basic stuff because it is a graphical user interface that you can just play with, play around with the blocks. You can drag and drop stuff and connect stuff together. Therefore, it's quite important because it's visual and it's simple. Therefore, most of the control engineers and most of the engineers with similar areas prefer Simulink. I myself also like Simulink, but I use it in a different way. And today I'm going to talk about that actually. And before I dive in directly into Simulink, what I'm going to do is I'm going to just show you some programmatic part where we can do basically similar stuff. And I'm also going to show you how to invoke Simulink using MATLAB code so that we can run multiple simulations using a Simulink model file and get the results and maybe plot them on a single plot. So I hope that this is basically a session where we learn stuff that we can use in the upcoming or in other lectures to use Simulink even more efficiently. So let's start with a state space realization example. We've worked with transfer functions thus far, but now we have a state space realization, which is basically a differential equation, but multiple differential equations with just order 1. So there's x1 dot equals x1 times, by the way, this is somehow not right. This should be on the right here. X1 dot is basically 1 times x1, 2 times x2 plus u. That's your first differential equation, and your second one is x2 dot is equal to minus 3x1 minus 4x2, and no input at all. So you have two different differential equations that model basically a second order differential equation. And this second order differential equation is most probably a second order transfer function. So what we're going to do is we're going to use a function called ODE, which is basically for ordinary differential equations. And we can use different ODE functions that are available in MATLAB to simulate differential equations or state space models, or even transfer functions for that matter. So let's basically create our data first. We have an A matrix here, which is 1, 2, minus 3, minus 4. And then we will have B here, which is 1, 0. And that's basically it. Now in MATLAB, what we can do and what is necessary for the ODE functions is to just come up with a function. So one way of doing that is basically writing the function down. So let's say function.m, and what we can do is we can write a function that returns basically the differential equation. And the way that we do this is basically just code an ordinary function that takes two parameters, namely t and x. And since we need a and b, we can also maybe include that, or just copy and paste this stuff here into the function. So, and the whole idea here behind this is basically to write this as a times x plus b times u. So this is basically the same equation as given here. Therefore, we need to code a function like this, ax plus bu. We're basically returning that. And yeah, I guess that should be it. So since we are interested in, did write it down. Since we're interested in the step response, here u can be just directly chosen as 1. So I'm going to just write this down as 1 because we are interested in step type inputs here. And that's basically it. If you call your function with a certain t value and let's say a certain x vector, you get directly another vector back. So this is basically going to be dx. And if you add this, or if you use this data and take numerical integration, for example, you would be able to just solve your differential equation. But we are going to use the continuous time differential equation solver And one of the most famous one, which is also used in Simulink, is basically ODE45. On the right bottom corner, you see the settings, which we are going to see. And there is just a gear or a settings button. When you click that, you can adjust the solver options, and one of the solvers is Runge-Kutta, which is ODE45. Now we have an explanation here. It takes in a function, it takes a time span, and it takes some initial values, which we have to provide in order to call this function. And the function returns basically the same data as the step function does. So we are going to use ODE45 in order to solve a differential equation, just like the step function. Now, the ODE function is function. The time span is going to be defined here. Let's define it from 0 with 0.1 steps up to 10. Let's have 10 seconds of simulation, and then some initial values. So let me call them x0 here. And the initial values are, for now, zeros and then 2,1. Because we don't have initial values in transfer functions, we might also prefer this to be the case here. So, and we get, and let me just wait on ODE45, hopefully, or maybe here. Why doesn't it show up? ODE45. And when I wait on it, here, t comma y. Okay, so t comma y. Let's call it x because our variable is in x. So when you do this and try to run it, let's see, run 1, you can see we have an issue here. And the input argument is not enough, etc. It complains about the function, but it's really not easy to pick up on what the problem here is, because we have a and we have t and x, even though we don't use t. We have ax plus bu where u is equal to 1. This can be calculated and this is returned. Why is this complaining? Well, you are providing the function, but ODE45 needs to have basically the function pointer, sort of, in order to be able to work with differential equations and functions. So if we look at help ODE45, probably we will see that there's an example where we use the @ sign here for the function in order to convert it into a function pointer. If you know C, you know what a pointer is. And here we can also see there's an @ sign here. And there are quite some ODE solutions or solvers here, but we actually need to provide the function pointer as it is shown here in the example. So let's do that. Let's provide an @ sign here. Let's run this, and we can see we have a t vector and we have an x vector here. So the nice thing about this is that we actually have solved x1 and x2, and the state variables, which we call x as the vector representation, consist of x1 and x2. You can see that the initial conditions start with 0 and 0, and then they evolve in small steps towards their final values, which seem to be 2 and minus 1.5 at the end of the day. So let's create actually a figure here. And hold on, let's plot. Maybe also use a grid on. And then t comma x. I'd say let's have all the rows and the first column. Let's give it a red color, line width of 2. And the second one in another color, maybe we should pick blue. We can also have a legend saying that this is x1, this is x2. Then we have also maybe an x label, which is time. And that should be it, actually. So when MATLAB is ready, we got the result here. Now, of course, we also can use the symbolic toolbox in order to come up with the symbolic expression of x1 and x2, and then plot them. But this is basically a differential equation solver. So what we can do is we can provide some inputs that correspond to time, and then get also that result. Maybe a cosine 2 times pi times t could be the input. Then we will see what the response looks like. And you can see now the system reacts to that. So basically, this is the easiest way of just solving a differential equation, an ordinary differential equation, because we have the ODE 45 function. And if we provide a function to it, we can basically use it like the step function that we use all the time. Now, the interesting thing that we can also do here, let me change this back to 1, so we are again looking at the step response here. You might not be comfortable with defining it internally in a function because you might want to change something about it, or you might want to use it externally. So what you can do is you can, of course, get the parameters using A and B, additional parameters. And what you can do is you can just wrap your function inside a new function. So what we can do is we can define functions, let's say function 2, using an @ sign, and then we don't give it a name because the name is already the variable here, and we provide some extra arguments like this. And what we can do is we can just define it like this. So the function body is here, the function arguments are here. This shows us that this will be a function pointer, and this is the function name. So this is a one-line, sort of a lambda function approach in MATLAB that we can use here. And let me show you that the function works actually. So function 2, 1, it needs also a t-value here. Function 1, 1 gives us basically 1. Why? Because we are providing x. So it's basically x, nothing else. Therefore, what we can do is we can use this to wrap another function in this function here. Since the ODE 45 here expects only t and x as parameters, as arguments, and since our function has 4 arguments, t, x, a, and b, we can just basically use this as t, x, a, and b. But this implementation here defines again another function which only depends on t and x. So what this line does is basically it substitutes a and b from these 2 values here and creates another anonymous function that depends only on t and x. So let me run it again. Now we see we have basically the response that we're looking for. Now, if I wouldn't do this and wouldn't do this, so let me basically comment this out, get rid of this. What happens if I just provide this here? Let's see. You can see it complains about the input arguments because our function takes 4 arguments, but the ODE 45 function expects us to provide only 2, namely t and x. So you have to create another function in a function, or a wrapper function in this case, t, x, and you're basically passing down t and x as the arguments, but then you're manually placing a and b here so that you have another function that has less amount of arguments and exactly the arguments that are necessary for the ODE 45 function here. Now, what we can do even further is the following. We can just take this implementation and ODE fun, that depends on t and x, and write it down like this. Then when we do this, we just pass ODE function here, and we don't even need to define this external function, which is quite nice because we have solved it in a single line here. And let me run it again. We have ODE function here. So dx should be, of course, erased here. So you can see it still works, but this is a one-line definition of the differential equation. So what we're basically doing is we're providing a function pointer to ODE45 because it's using the right-hand side of our differential equation. In this case, it has two rows here because it has two differential equations here of order 1. So this is basically one of the ways of solving it. And I've talked about different solvers here. So what you can do is you can maybe pick ODE23 and see how we can use that. So let me see here. So it has basically the same usage here. Let me see. Yeah, so we can also skip to ODE23 here because we're using them like this. So you can switch around differential equation solvers. And if you're just looking for differential equation solutions, you don't really need Simulink. If you have ODE function and provide a function, you're good to go. You can do whatever you want. Of course, Simulink has some other capabilities. Therefore, you might prefer it. But if you're just simply looking for the solution, you can just use the solver function directly from MATLAB. The advantage here would be exporting and moving the data is not necessary because you already have them in your workspace. What happens is that Simulink has some internal signals. Sometimes we want to combine them using figures and plots and maybe export them. What we can do is here, we can just print and then give it a name like ode.png. And then dpng, if you provide this -dpng, it will basically print it like a PNG. You can even assign it a resolution here. When you do this and run it again, you will see on the left in my Explorer, a PNG file is created, and you can see you have this nice export here. Most of the time, when you're in Simulink, you are using the scope for this, and then you can just print that into a figure, etc. But if it's just simply about the ODE function here, why not use MATLAB itself? Because we can. Now, since we have this, what we also can do is we can convert this into a transfer function and use the step function here. So if you want to check if it's working or not, let me just place this here and get rid of this, probably leave that one probably. So we've solved using the ODE function here. So let's repeat this for the step function here. So t, y, or let's also call it x, and then step. We need a GS, and then we also have t here, and then we can just plot it like that. So maybe we should give it like a dashed line here, and then 1,5 or 1.5 in order to see being able to see the plots. Now, what will GS going to be? Well, we can use basically SS here, state space, and then we provide A and B. Now, usually the state space realizations are in this format, AX plus BU, and then Y equals CX plus DU. Now, that's actually the state space representation of a system, of a transfer function, of a differential equation. But here we don't have really C and T, we have only dx, ax plus bu, and we're interested in all the states because we're plotting all the states here. So what we can do is we can choose directly y equals x, so the output should be all the states. And when we're doing this, we're basically saying that we have an identity matrix times x plus 0s 2, 1. If I'm not mistaken. Yeah. Why? Because this will be a single input, multi-output system in this case. So we can use this in order to define our system. Now I'm going to use C as identity and D as 0s 2, 1. And if you're really interested in the transfer function, as far as I know, you can just go ahead and wrap it around a TF in order to see what it looks like in transfer function notation. Now you can see we have basically one input, but two outputs here. One of the outputs look like this, and the other one looks like this. And the reason for that is we've basically used a C matrix that looks like this here. It has two states here, but the outputs are also two, namely state 1 and state 2 here. So if I have the transfer function, it doesn't really matter if it's a single input, single output system or a MIMO system. We will get basically the step response out of this. So let's run it. Maybe in line 18 and 19, we could see some problems here because maybe the structure is different, but we'll see. Yeah, if we look at X, it's just a single thing here, which it shouldn't actually. Did we do something wrong here? Let's see. Let's why is X like that? So let me just call this here. Inval final time or vector time steps. Let's actually don't plot first and see what the result is going to be. So run one, size of X. Interesting. Size of T. Okay, we have an inconsistency here. It should be X comma T here, so that we get basically the outputs here. So interesting that the ODE function returns it in an inverse order, whereas the step function returns it like that. So let's see. Let's also plot it. There we go. Now, of course, it's not a good idea to have both the same color. So let's see. Now we can see there are some lines here. I don't know if it's obvious. Let me try to make it obvious here. If I, for example, zoom in here, you can see there's this dashed line here. And there's a slight difference, but that's okay because we're solving for differential equations. These slight differences occur. We have to tune this basically. Maybe we have to provide a better sampling time here to get better results, or sometimes we need to change also the ODE solvers here. So let me try it again. And let's see if it's distinguishable now. Now they're even more close to each other. We can see that they're almost the same. There's still some offset here, but you can see the offset is not really that important. Now, what we've done so far is basically we have solved a differential equation using the step function itself or the ODE function, and we've compared them. And we've seen that at this point, we can use MATLAB's code in order to simulate a certain dynamic system or differential equation. So that's part one. Let's repeat this stuff for Simulink. Let me invoke Simulink by just writing down Simulink and entering it. It should open up a window. And it's initializing here. So now this is the screen that welcomes you. And we're basically just creating a blank model here. And Simulink is going to start. Hopefully. Another fact that I don't really like about Simulink is that it is fairly slow. It depends on the version of MATLAB and Simulink and your computer specifications. when you're running Simulink, you need a quite powerful computer for that. So yeah. Now this was the solver that I was talking about, and you can see it is just a variable solver and stuff. We have to, most of the time, we have to go ahead and adjust this. If you click on that, you can here solve using fixed step or variable step. I prefer to go with a fixed step solver, and from the fixed step solvers, you can see I'm using ODE4 or ODE45 here. I'm going to leave the sampling time here, but you can go ahead and adjust that if you want to. If you're running in trouble or if your graphics are not really that smooth, you have to maybe change the solver or the sampling time of your solver. But keep in mind that if you want quality, you will need some computation time. If you need speed, then you will lose quality. So there's a trade-off. And the same it goes for this code too. If you just have a finer grid, a high resolution time vector here, the result will look better, but it will take more time to solve this basically differential equation. Now, the nice thing about Simulink is that you can just go ahead and search by just writing down, for example, if I hit somewhere and go state and then space, it will directly give you some suggestions. In this case, I'm interested in this state space model here because we're interested in Simulink in state space models here. And what we can do is we can just go ahead and type in the values into here. So we have basically 1, 2, -3, -4 as an A value here. And then the B value will be also a vector, a column vector here. Now, at this point, I'm going to give you an advice if you're using the state space block. And if you're interested in state space simulations, sometimes for probably if you're, for example, using a state feedback controller, which basically uses this states to feed it back like a p-type controller. If it's an LQR, if it's something like that, it's probably needing these states. And if you have a certain transfer function, you will have, for example, a SISO system, single input, single output, then you are not able to basically reach these states because they are internal here. You can see that the input is U and the output is Y, and everything in between is internal. So X is internal. So what I see most of the time students do is that they use just directly the integrator block, and they construct the system from scratch. Now, is that really necessary? Actually, it is not. You can get rid of those unnecessary integrators, and if you have a fifth order, for example, they place in 5 of them, and then there are some multiplications and summations, and it becomes too complex. At this point, instead of doing that, what you can do is you can just choose your output to be only the states, then you can construct the output yourself, and you're good to go. What I mean by that is that, and we've already done that in the code piece here, so zeros 2, 1 here. And of course, we have no initial conditions, apply. Okay. Now, even though it doesn't seem like that, we have actually 2 outputs here. And the way we can basically look at that is using a demux. So demux is basically, if you know logic, you know what it basically does. But this one here is basically to convert a single line, which you know it is a multiple single line or bus. You're basically extracting the signals here. So if we have 2 outputs, then you can specify the number of outputs here. And we have 2, so you can just basically access x1 and x2 like you want. So we need to add actually a unit step function. So I'm going to add in a step here and connect it to this. And then we also need maybe a scope in order to see what's going on. And in your scope, what you still can do is you can double click it and maybe change its appearance, its style, or you can actually right click on it. And then you have some thing called signals and ports, number of input ports. I'm going to change it to 2. So I have right-clicked it. I've come down to signal ports, number of inputs. I've changed it to 2. So this way I can basically just do it like this. Of course, you might argue you can just delete this, directly go ahead and connect them directly, but I like to just separate stuff, and maybe you can even go ahead and name them. So that's X1, and this should be X2. Now this is going to be U, and there we go. If you hit space, it will just center it on the screen, on the visible screen here. Now let's actually call it model.slx. And there we go, we have an SLX file. Now, I have saved it, but if you're sharing Simulink files, you will run into a certain problem, which is versioning here. MATLAB does not really do a good job in versioning here, if you ask me. I find it too troublesome. Maybe there's a quick fix for it, but, and I don't know. If please just inform me. But if you have an older version and someone gives you a newer version saved Simulink file, then most of the time you're not able to open it. Of course, everyone can open the old Simulink file, but if it's a newer version than yours, then you cannot open it. I've faced it many, many times. Of course, there's a fix for it. You have to save it differently. So I guess under save, there should be something called export here. Is there something like that? No. How did we export it? I don't even remember. Under simulation modeling format, well, there should be something like export here, but maybe I'm missing something. So let's make it full screen. No, I cannot see it. Oh, yeah. Well, under save as, there's this version. Is there versioning? Nope. But yeah, where was this? I definitely don't remember it. Model settings. Nope. Yeah. Yeah, I don't even remember where to do this. Interesting. Yeah. Usually it should be here. Oh yeah, there we go. Sometimes the menus change. Export model to, okay. You can export it to a previous version here. Then you're going to save it for that version here. And you can see what I mean by that. If someone uses any, maybe the newest one, mine is to 2020 A or B, something like that. So yeah, you can save it in an older version to ensure that the one that you submit this file can open it. But other than that, Simulink is quite powerful because we didn't write any code, and we're ready to simulate systems and differential equations at this point. Let's hit run here. And it solves it. And when we click the scope, we get basically the same data here. Of course, since we have this unit step function, you can see that the step time here is 1 and the final value is 1. So it starts from 0, and at t equals 1, it just goes up and shows you the complete effect of that. You can see it waits 1 second and then applies step, so you can see what's really going on. If you don't want that, you can go ahead and change the step time to 0. Then it will basically be the same or look the same. There it starts at 0. What you also can do, and what I like to do, if you're going to use Simulink, and if you're writing your thesis, dissertation, or if you're writing a report, preparing a report, or even your presentations, what I would highly suggest to you is to change its styling here. Because if you're projecting this on a wall or on somewhere, these black lines this black background and these line width here will not be visible. You can be sure that they will not be visible through a projector because it uses some pixels, and the darker most of the pixels are, the lower the quality will be, at least at our university. So you should be changing the whole thing here. Now, what you can do is you can just update one of the scopes and the style of one of the scopes. And if you copy and paste that scope, every scope will share basically the same here, the styling here. Now, let's toy around with that. Let's apply that, for example. Now you can see that the borders are white. You can change the axis colors here. Apply that. Now you have this white background here. You might want to have a better grid color here to have more visible stuff here. That's also okay. Now for X1, since we have only 2 signals in this case, we can change the line width to 2, which I programmatically do most of the time. And yellow is not the best color here. So maybe we should start out with red. And yeah, we can change to X2 and give it a nice blue color here. So you have to increase the contrast in order to be sure that your stuff is visible. Now, if you hit OK, you're good to go. Now, this looks more like it because if you have a projector, this whole thing here will be more visible. And if you're printing it out, this will save you some ink. Now, once you have that, you can copy and paste it and the scope will preserve that. If you don't specify the number of inputs, you can just change all the channels on the scope and then use that like you want. Now, of course, I have coded in the A, B, C, and D values. You don't really have to do that. You can just place in A, so the variables themselves, and when you run it, and if they're defined in the workspace, then you're good to go. But I'd like to keep it like this because I'm going to do that from my code here. So we've saved it. Now let's see. We have basically repeated the same step. You can see it's much, much more easier. But if you want to print this out, for example, you can actually print this to a figure, or maybe use a print or copy to clipboard. I don't know if copy to clipboard works. So let me just try Paint here. It does. So you can use Paint here and copy and paste it. But what you can also do is you can just print it to a figure. So File and then Print to a figure. It will just create you figure 2. Now you can go ahead and basically just save this as a figure. So in your code, you have basically this here. So if you say figure, so let me just code it here. If you write something like this here and enter this, you will see that the figure is also saved. So it doesn't really matter where the figure comes from. You can go ahead and use this print function here. By the way, this is using like using a printer, but you are choosing the printer that will generate a PNG file. So D is for device, so device PNG here, and R is for resolution, so you can increase the resolution, and you have the file name here. So, there we go. Now, let's actually move on. Now, since we have all this stuff here, let's use some mux blocks and export the simulation data and repeat A. So by this, what we mean here is to export data so we can access them numerically in the MATLAB environment here. So we have this, instead of plotting this to a scope, so I'm going to remove all this stuff here. Instead of exporting this to a scope, what we can do is we can use a to workspace or to file. So let me go with to file here. So this is basically exporting the data into a file. And you can just say results.mat and variable name, let's call it data. So you can adjust some stuff about that. If you want to have time series, if you want to have array, for example, it changes the usage. We'll see decimation sample time. I'm not touching that. So I have that, just that. Here, what we can also do, and which is quite nice, which is like commenting out a block of code, you can go ahead and, if I can see it, there we go. You can comment out blocks. So MATLAB or Simulink, at least, doesn't warn you about the unconnected ports of certain stuff. So if I run this, you will see on the left, now we have something called results.mat. Now, I can load and I can save mat files. So help load. Now, you can see that in the examples, you can use the file name and then load and then a variable name, so you can store the whole thing into a variable. So this becomes quite handy because what we can do is we can do something like this. Let's say if false, and let's put that aside. Let's just place that there. And all this plotting here, and then else, and then end, and then print ode.png. So I've placed the if false block here, which technically gets rid of this here, but I didn't comment out. What you can do is you can comment it out and just comment it back. But I like to use some trivial if blocks sometimes. If I choose it to be true, I'm using something else. I'm using the pure MATLAB code approach. If I'm using false, then I'm using basically Simulink for this case. So here I will say data, or maybe mat file, let's call it that. And then I'm going to use load, and we have results.mat here. So I'm going to look at the internals of mat file. I want to see what's really in there. So before I do that, let me just invoke the MATLAB simulation here and save it. So my ODE.png is going to come from the MATLAB part here. Now, let's convert this into a false statement so that this one is skipped, and I'm looking at this. Of course, for mine, I have to run it twice because, yeah, this environment here does this. And now we have something called data in it. So you can also maybe call it results. So we will have result.data because it's a struct. And we can see that it's something called time series, where you can get the time vector out of it by just using time. And then there's something called data within capital D. You have two signals here, and you already guessed it. It is going to be your x vectors here. So results.time should give you actually time. So t is equal to this one here. And x is going to be data here. So let's run it again. So time and x is our data. How nice is that? Now what we can again do then is we can go ahead and create our own plot and then save it like ODE_Simulink. Very nice. So there we go. Now we have the ODE Simulink part. Of course, we have a different coloring scheme here. So let's change that. There we go. Of course, line width to would suit me better. Of course, you can also compare them on top of each other, but I'm not really interested in that at the moment. Now, you might ask yourself why we use that. Well, I like to use Simulink like architectural data. If you have something to simulate, and if it's a complex system, then you should go with basically this approach where we just think that this is basically the architecture, and I'm going to provide the necessary data at the necessary places externally, and I'm going to get the inputs and outputs on all the visual or all the numerical data also externally, and everything else should happen in Simulink. So in my opinion, if you are working with a complex simulation, then you should go this route. If it's simple and if it's fitting just one Simulink file and one page, then you should do whatever you want. But if it's complex, if you have like a simulation of the drone or simulation of a certain complex system, for example, then you should be a little bit more systematic in terms of using Simulink, because at some point it gets out of control. So we have basically exported it. We don't really have to export it with two file. So convert it into a two file. We can also use two workspace here. That's also another option that will basically save it in this variable with, again, the time series into the workspace. So just to show you that that's the case, I'm just going to connect the same thing here, and I'm going to run it here. I guess it is called SimOut now, or out. Well, that's it. Now it's out.simout for the time data, actually the whole data here. So you should call it out.simout.something, well, probably data here. There we go. And maybe time. Was it called time? And there we go. So you can save it into a file. You can save it into the workspace in order to get the outputs here. So that's also another approach. And I'm going to delete it. You can use arrays and stuff. You can use time series, whichever you want. Now, we have actually used some mux blocks and we have exported the simulation data. Now, what you can also do, of course, I didn't do that part, but you can use a mux here, which is the inverse of a demux, which will create just one single root out of basically multiple data here. So what I can do is I can just basically take the input here, and in order to change the step type, I'm going to change the step time here. I'm going to delete this. Now I'm going to connect this to the results. Now, this is what I mean by exporting everything here, because now I have all the signals, all the internal signals that I want to use here. Now, in order to complete the example that I gave you, if you're using state space and if you want to, for example, create a C vector and D vector here and create an output out of the states, let's assume that this is going to be, oh, we need a demux, by the way. So, yeah, let's change it a bit to have more fun. Let me take this whole thing here. There we go. So I'm going to use a demux here to complete the example that I was trying to give. So using the demux, I know that I have two states, so there is one input, two outputs. Let's assume that, by the way, you can also rotate stuff here. So let's rotate it, I guess, clockwise. There we go. Now, I have copied and pasted this. So let's assume that this is 1 and this is 2, basically. So this is 1 times x1 and 2 times x2. Let's have a summation point, and let's have basically just plus plus. Maybe return this one also clockwise to get nice and organized. There we go. Now, if d is 0, then you can use that, but let's assume that our d is not 0. So counterclockwise to have this one here again. Let's have d equals 1 here. And let's add another summation. You can combine these summation points here, but I'm going to do it like this. So there we go. Now this basically is the output y. Let's have the input, output, and all the states. So I'm going to export everything out of this Simulink file here. So I guess we need 4 inputs in this case. And let's have a strategy. Let's say first we're going to go with the input, then we are going to go with the output, and then we want to have this first state, and then we want to have the second state. You can also give it some names. So this is basically x1, this is basically x2, this is u here, it shows up itself, and this is called y, in order to inform yourself that u, y, x1, and x2 will be basically the whole thing here. Now, in our code, what we are going to do, we are taking that, we have the data here. So let's call it, again, data. Now, I know that the first column will be u, so I can just recreate the same signals here. So the first column is going to be u, the second column will be y, and then the third column will be x1, and then the fourth column will be, actually x2 will be the fourth column here. And what you can do is you can create maybe a subplot here, but I'm not going to do it. Let's just use some colors to indicate them. So let's have input, this, maybe also some display names. And let's have also a title here. State space simulation. Let's give it a display name. Therefore, we are going to give it a legend, show. And there's also something called location. And you can just choose the best location so it doesn't hide data behind it. So this is going to be u. Let me get rid of that. Let's call it state space Simulink PNG, something like that. So the second one was y. Let's have this red. Let's have x1. Let's have this magenta. Let's have red and blue. And of course, the according names, y, x1, maybe an underscore, x_2, and we should be good to go. Of course, we first have to run this, and then we're going to basically run this one here. There we go. We have the perfect export and image creation even, because you also have the same here. And you see we have the step function here, and then our output just rises up, goes down like this. It is created from these two states here, the sum of them, 1 times this one here, 2 times this one, plus the input itself gives you that. And if you find it strange, that's just because of this one here. If we change it to 0, run it, run this again, we can see it updated. Now the input is not included, and therefore the system behavior is just the weighted average of these two signals, and you get this result. And you can see that the location best basically searches for an empty space and places the legend there. You can see the colors, you can see everything, and I find it quite nice to use this in order to export Simulink data, because at this point, what I'm going to just care about is to rerun it, and it will just create the according PNG files. And when I'm creating a report, I most of the time use LaTeX, and I can just show this path to LaTeX, and it will just update it. So being organized can help you out in the effort part. So that's of course not all of it. What we can still do is, now we have done this so far, and here what we can do is we can use a p-type controller and then a closed loop, reference, error, control input, output signals. Basically, I'm going to do the same stuff for a unit feedback, which would be a bit more familiar with U. So let me actually create another one here, new blank model here. Let's call this something like model P for P controller, maybe. And let me close this one here. There we go. So in a classical unit feedback, we have a summation point. Start with a sum here. Of course, the second one should be a negative sign. Let's update that. There we go. Then we will have the gain, which is the p-type controller. Let's connect it there. Let's call it the gain. You can also call it controller, whatever. There we go. Then we have a transfer function. There we go. Which I'm going to leave it as it is. And I'm going to call it the system, maybe plant, maybe something else. It's not really that important. Now I'm going to connect a step function here. There we go. Connect it there. And we will also connect this thing here. Now we know that this is basically the reference, and then we have the error, and then the control signal, and then the system output. And we might be interested in all of them. So I'm going to use a mux here again. And I guess we have 4 signals here that are important. And I'm going to connect them in order. So R, or the reference here, and then let's have the error here, and then the control signal here, and then the output itself. And let's have to file again. Let's call it, I don't know, results P. And let's actually call it data, and don't change anything else. So that's quite nice. Now, what I'm going to do is I'm just going to run this for now. I guess it should work because 1 divided by s plus 1 divided by 1 plus 1 divided by s plus 1 should give us 1 divided by s plus 2. So we should have a stable closed loop here. And it should work basically. So let me just get this part here and open up another run file, run2.m. Go up to this point here, clear CLC. And now we have the results. Of course, if you're using Workspace, you shouldn't clear because you're getting rid of the workspace. As a quick note, so it's called results_p. And we should have that actually here. There we go. That's it. And we called the thing here data. But let's see. Let's actually invoke this part here and see what the result has. It has result.data. So what is result.data? You can see we have time. So this one should work. And then we have data. This should also work. Now, the first one was basically the reference. The second one was the error signal. The third one was the control signal. And the last one was basically Y. So I'm going to basically change these. R, reference, output, and then the error signal could stay like that, I don't know. And then the control signal. And one of them will not be visible because there is a ratio 1 between E and U, so they will be on top of each other, but we will quickly fix that. There we go. So this is reference. Now this is basically simulation P, something like that. So if I run it, again, we see the result here. This is not the result that we're after. Maybe we should take this one here. So it's not going to be that. It's going to be P controller. I guess everything else should be the same. Oh, you're running basically, yeah. We should be running run too. So there we go. Now it's a bit interesting, of course, but we're combining everything on top of each other. So that's basically the reason why. And you can see that it is a stable closed loop here. We should be plotting the output at the end in order to have it on top of everything here. There we go. Now, of course, at this point, I'm doing the following. The way that I'm simulating stuff here is I come here, I run this part, and then I go ahead and run the code here. There's nothing wrong with that, but what we can do is we can just get rid of the Simulink part and not even see Simulink in order to invoke Simulink. So we can do that by, first of all, specifying the file name here. So I'm interested in basically the model name here. So the model is called model_p. And then I am going to run a function called open system here. Open system here. You can see this is basically the Simulink interface for programmers. For those who don't want to basically use the graphical user interface, what you can do is you can just use open system here. And we will give it basically the model name here. And we can actually give it another argument, which is called load only. And I'm going to close this one here. We saved it. Just close it. I have basically closed Simulink now. I have nothing here. I'm going to clear everything. We're starting out clean. So let me comment out everything and let's go. Now, if you call open system with load only, without load only, it will just open it up. Let me first show you that. So run to, there we go. You can see that we can invoke Simulink from the code. But if I do something like load only, and if I run it, it will not show up, but it will be opened up behind the scenes. Now, let me also define another transfer function here, tf 1, 1, 2 perhaps. Now, this is going to be the transfer function in the model itself. I have something called system in the model, and I'm going to use this data in order to fill out that one here. And the nice thing about that is, about Simulink and about this interface, is that we can use something called setParam, for example, which is again a Simulink interface function. And we can use the object and the parameter name and the value. And there's a lot of documentation about it and stuff to try out. But I'm going to show you the simplest ones that will save basically the day here. Now, the way that we are going to access stuff is we're going to use this name. And for example, if let me open up the Simulink part here again. So let's actually get rid of load only. Let's open up the system here. There we go. That's the system. Now I will use the model _p as the name, and then slash, and then the name that I gave here. For example, for the gain, I can use /gain in order to access this object here. I can also use /system in order to access this one here. And then if I double click it, I can see that there's this property called gain. I will change the gain and give it a value, and I will set it up. So let's try, first of all, using setParam, and it will be something like the model, and then slash, like this, and then let's call it gain. Now the parameter name is going to be gain. So I'm changing the property gain, and I'm going to give it a value. But keep in mind that the value should be basically a string. So everything is in string here. Num to str, let's call it kp and semicolon. And I'm going to define something like 2 here. So let's actually run this. Num str, it's called num to str. There we go. And there we go. I didn't touch the Simulink interface. I didn't put in this value manually, but you can see that I have changed it. Just using the code and just navigating through the objects with this set param here. So you have a object string and it is hierarchical. Therefore, you give the model name and then slash, and then you navigate to the gain. And it has the property gain, and I'm going to provide the string representation of the value that I want to put there. So if I have a for loop, I can use set param and I can change it over a for loop, and this opens up interesting opportunities for us, in my opinion. Now, what about the system itself? Now, I can access system here because we have the system here. And if I double click it, I can see that actually we have the numerator and denominator, and they should be in vector format. And I can generate this basically. And if I access the numerator here, so system, and then I'm going to call it numerator. It's not case sensitive as far as I know, but the only thing here is to generate the according vector here, nothing else. So if you can generate the vector, you should be good to go. Now, we know that we can basically use gs.numerator, and then this one here, of course, we are working with syso. And if I create this here as a string, I get basically this result here. The only thing that is left is the parentheses. So I can add them manually so that we will have a opening bracket here and then a closing bracket here. And there we go. Now I'm going to check the string. Now you can see I would have put this into the graphical user interface here. You see we have basically brackets here, and between the brackets we have basically the coefficients here. So I can do the same for this one here. So let's change the numerator and then the denominator and then the denominator. There we go. So we should have changed that. So run two again. There we go. Now, the nice thing about this is I am basically using this model remotely. I'm just changing the values as I want them, and I'm not using Simulink at all. The nice thing about this, of course, is, and I'm repeating it myself, but the nice thing is that I'm just changing it via code. And if you're interested in different parameters, you can just write your code accordingly, export the graphical data, or you can save them under different names probably, and then combine them later and do some crazy stuff about them. So we can also change other stuff. For example, this would be a one-time change, but still. Now we're giving the model itself at this point, but I can change the solver. And let's change the solver to ODE 4. So I'm also accessing that data here, ODE 4. And I can change the start time. Start time. And then it could be 0. I can also change the stop time here. Let's, for example, have 5. The only thing that you should remember is when you're using set param, you're using basically string data. Everything that is numerical should be converted into string. And if it's messing up stuff, that's your fault. You should be cautious about it. You should be the one that is responsible to provide or feed the right data, the actual data. Now, let's also maybe change the solver type into fixed step. So I'm just doing it like this. And we can also change the fixed step into 0.001. Let's get rid of that. You can also embed some start function here. And the start function will be basically, again, a string. So you can call a MATLAB code from there. And it could be something along the lines of simulation starting, maybe. And then, of course, you have also a stop function here that says maybe simulation finished. Then just one dot here. Now, what you can do is you can also save the system, which is, again, something like set param or stuff like that, and just call MDL so the changes take effect. So there we go. We have actually changed stuff, and you can see it is ODE 4, and the step size that we're looking for is 10 to the power of -3 here. So the only thing left now would be to run the simulation. Once we've saved it, we can just call sim and MDL. And does it show us that one here? So we have actually, where is it? Simulink sim. You can see that it simulates the specified model using existing model configuration parameters and returns the result as either a Simulink simulation output object or as time vector compatible stuff, and so on and so forth. Of course, I'm already exporting stuff, so I don't really need that. I can then close the system, MDL, and then I can run this part here. So there we go. I'm still opening the system and closing the system. You can see simulation start, simulation finished, and it should have popped up and just gone away. So let me just do it like this. It comes and goes. Let me just repeat it again. It comes, it simulates, and it goes. And you have also this notification because we have altered the start function, stop function. So we can see that starting, it's finished, and we have also the results here. There we go. We can see that if we increase, for example, the gain a little bit more, let's have that in front of us. We can see it has an immediate effect. The error goes, but we can see, for example, increasing the gain of the p-type controller, using a high gain for the p-type controller decreases the steady state error, and we can see that using Simulink and using code and coding that for Simulink. This part is actually quite important. So what we can do is we can do also another application. Let's also do that one and conclude our today's discussion. I have shown you a piece of code which is quite easy at this point, because you will always use some default blocks for simple simulation. If it's complicated, I don't know how setparam does support it or how Simulink will react. Let me also show this part here. So you should experiment with it. But you can see it still shows up and vanishes. Now, when I do it, it doesn't show Simulink at all. So you can just hide Simulink behind the scenes because you have only loaded into memory and you have simulated it. So let's return back to 1, for example. And there we go. So this is quite nice. We can change the system, we can change the gain, and we can see what's really going on. So we have another application here. Let's quickly do that. Now, here we are asked to use a sine wave and calculate the amplification, plot the amplification versus the frequency. So that's going to be our task here. So let me just invoke Simulink again, create a blank model. Now, so let's pick up a source. Yeah. Simulink, that's not going to be it. Random source, current source, voltage source. Yeah, we have lots of sources, I guess. Sinusoidal force flux, nope. We almost had it. I guess it's a good time to demonstrate the library browser here, which I'm not using often, but actually I'm looking for a specific source, which is a sinusoidal wave. Actually, yeah. Where is it? Now, maybe in commonly used blocks. Nope. Maybe sources. And then sine wave. It's called sine wave. I don't remember that it is called sine wave, but yeah. Let's pick this one here. I guess this one is it. There we go. Yeah, this one should be it. So we have the source here. Now we need a system. Actually, it's called a transfer function. Transfer function. Let's again call it system. Let's call this one the source. And now we're connecting it to that. And then we have a mux here. And then we will have basically the input and the output. And of course, we are going to use it. Well, we could use two Workspace to show this one too. There we go. So let's call it data here as time series, and that's it basically. Now let's call it model frequency. Model frequency, there we go. Now source and system will be the stuff that I'm going to be interested in. So maybe let's copy run 2 here, call it run 3. So now this is going to be model frequency. And we're only going to load it. We will have a certain transfer function. We don't have KP anymore. We can set up the transfer function, not the gain. The solver type seems okay. Simulation seems okay. At this point, the result, it's not going to be like this. So I'm just going to temporarily fix that. So amplification of GS frequency versus, was it that? So the sine wave to a system and calculate the amplification. Amplification versus frequency. Yep. So yeah. Now, we are going to basically look for just one change. So let me just go ahead and look for it. So we're going to use setParam, but on the source. And yeah, I guess I have to open it up back again. Let's open this one here. Now, if I double click source, we have the amplitude, we have bias, we have frequency, and it's in radians per second. So I'm interested in this frequency here. So basically it's going to be frequency. So let's call it frequency. And the value will be basically just one, a scalar value here. So it's going to be num to str, but it will be something like omega here. Of course, the interesting stuff about this is the following. We will set this just one time. The system will stay the same, but this frequency will change. And I'm not going to close it until I'm done with it. I'm going to simulate it. And yeah, let's have a omega vector here. Let's change it from 0.1 up to 0.1 up to 0.2, for example. And let's also go ahead and look for a certain gain value. So the idea is the following. I'm going to change the frequency of the sine wave that is given here. I have already inputted my system here. And then I'm going to change the frequency and look what the gain here is going to be. That's basically the whole idea here. I'm going to look for the peak value, because this is kind of the Bode diagram, but I'm generating it using the Simulink. The Bode gain plots, I'm going to use Simulink for simulational data, and I'm going to generate the Bode gain plot, basically, or the amplification. So in order to do that, I have to run multiple simulations. So that's why we have this example here. I'm going to use the same size as omega vec, because I'm going to try one value for omega vec, compute the whole stuff, get the gain, and save it to this vector here. So we've generated that. Now there's going to be a for loop, length omega vec. I'm going to run this stuff in a for loop. Now we're basically calling Simulink in a for loop. So set the param to this. It should be omega vec I in this case, because it's going to be ith value of omega. And then we're going to simulate that. I'm not sure if we really have to save the system here. We don't really have to save the system. It should work right out the bat. And it's going to be out.data, isn't it? Out.data. I'm going to see what the internals are going to be. And I'm going to close this. So let's run 3. Now, unable to resolve the name. Maybe it's going to be out. What was the name of it? Well, we called it data. So maybe it's data. So we should have simulated it. There shouldn't be a problem at all. The system is updated. The solver is updated. The only problem here is that I need to access that. So we're in run 3. Out. Data. Interesting. Why isn't it showing up? So if I run this, so it is out. It is going to be out.data. Interesting. Out.tout is going to be the whole time vector. So I'm actually not really interested in time data here. Out.data. I don't know why we mess up stuff here. And then .data here. Out.data.data is going to be basically the data here that I'm going to be interested in. And the second one, the first one is the source. The second one is going to be the output. So this is basically the output here, y. And I guess I'm going to be interested in max y. So let's see if it's running. Unable to resolve the name out data. Why isn't it working? Why did we mess up when we use that? Interesting. Why isn't it? Unable to resolve name out.data. Something is not quite right, but I don't know why. And it's also not generating out, I guess. Unrecognized function real out. Why did we run into trouble when we are? It's also not data. What about sim out? No, it's not working. So yeah, let's try this out. What about sim out like that? Now we have sim out. Interesting. Sometimes it baffles me, but yeah, we've solved basically the problem now. Now we can use SimOut.data as far as I'm concerned, and maybe the maximum value here. So let's try it again. Now we have the values. And basically, since we have the values here, we can save it to gain I equals maximum of Y. Since we have a unit input, we don't have to divide it. So basically, the theory behind this is, let me just open Simulink and the model frequency here. So the idea behind this is the following. If we apply some sinusoidal wave from the input, since this is a linear time invariant system, it will change its gain and phase data. And we can calculate the gain, the maximum amplification, when we have the input and output. If everything is at rest, the ratio between the maximum value of the output divided by the maximum value of the input. Since it's a sine wave, it's just going to be 1. And since this one is also going to be a sine wave, but it will have a different amplitude, we're looking for the maximum value of this signal over time. And once we've found that, we're just basically changing the frequency again, and we are going to plot it versus the frequency. So the amplification versus frequency will be the body's gain plot here. Now, we basically, when we run it, we have that data already. So let me just plot it here. It's going to be amplification and stuff like that. And we don't really need this stuff here. We just need one plot. It's going to be omega vec versus gain. And that's basically it. We don't really need a legend here. Going to skip that too. Basically, Y label is going to be the gain here. So run 3. So it started and finished, and we have 2 values for that. Now we need to change it, for example, up to 10 here, and see what's going on at this point. Of course, there are multiple simulations. So this is basically a nice way of using Simulink. We've coded it. It will try out the whole vector. This wouldn't be possible using basically Simulink on its own. Without code assistance, this wouldn't be the case because we've tried it out and we have got this. Now, a slight issue with this would be probably the fact that for low frequencies, we need more settling time. whereas our settling time or our simulation time here is basically just 10 seconds. What I would rather do is I would just give it a more optimum stop time here. I'm not quite sure how long this one takes. Therefore, let's do it for better frequencies like 1. Or let's use log space here to be a bit logarithmic here. Let's use 0 up to maybe, I guess 2 here. And then maybe like 50 simulations, and that's it, basically. I can also use something like set GCA X scale, which we use a lot for body plots, log, so that the scaling is also logarithmic. There we go. Yeah, we have a portion of our body plot attempt here. I'm not quite sure. We can check if it's correct, but of course, if it's not, the problem would be probably about the stop time here. But we can use basically a mag and then phase and then omega and then call body on our transfer function with omega vec. So we have the same vector here, and plot maybe omega vec and then mag squeeze mag here, so we get rid of the extra dimensions, and then maybe in red with line with 1, so we can see the difference here. Yeah, let's run it basically. Let's run it again and see how well it does in terms of stop time here. We might need to increase the stop time, but other than that, we should be good to go. You can see we're slightly off here. This would be the ideal case. This is basically our methods. We need to maybe increase the stop time a little bit. If that's not cutting it, we might also need to increase the step time here, fixed step solver time, in order to increase it. Let's see how well we approximate that. Well, still the same. Let's try something interesting. Let's try the limits of our computer. It takes not that much, so we can test it. Of course, it should be in steady state. So instead of doing this, we need a little bit more additional code, because in the transients, it might be the case that the peak is even higher than it is. It might be because of that. So what we should really do is we should cut maybe the whole thing into 2 and then look for basically the peak value here. So let's see if it's 0.01. If we have, do we have t? So yeah, what is the length of y here? So let's divide it into 2. So it should be 5,000. So instead of looking for the maximum value from there, let's assume that we're looking at the second half of our sine wave, because the first part will have some transients in it. Maybe that's going to fix it, maybe not. But you see that the idea behind this is we can use Simulink here. And by the way, it's using an autosave also, but yeah, not that important. if we use save system here, we would like, there we go. That does the job. If we use save system, we would slow down the whole program because it would save to the hard disk and then it will save over and over like 5,000 or 10,000 times. That would be not a good idea. So that's why I have moved it down here. And you can see we can basically match the whole body plot, and the way that we've accomplished this is basically using Simulink, the sine wave, and the transfer function itself. Here I have simulated the same Simulink file for different parameters 50 times, so you can do that too. So it's a nice tool. Hope that this lesson was helpful. See you in the upcoming videos.